Find the minimum height of the building, h, in feet, such that the p delta effects are not required to be considered. In this problem, a building of an unknown height, h, is loaded down with 200 kips. The building is an office building constructed with a special moment-resisting steel frame. The seismic design category, seismic response coefficient, and maximum inelastic drift are also provided. P delta effects are not required to be considered in a seismic analysis when the stability coefficient, theta, is at most 0.10. The stability coefficient equals the total vertical design load, P, times the elastic story drift, delta, divided by the quantity the lateral seismic shear force, Vx, times the height of the structure, h, times the deflection amplification factor, CD. Since the question asks to find the height, h is isolated on the left-hand side of the equation, and the stability coefficient will be assigned the value of 0.10. Since 0.10 is the largest stability coefficient, such that the p delta effects are not required to be considered, and will therefore minimize the value of h. From the problem statement, we know the load P equals 200 kips. The elastic story drift in this equation, capital delta, is the same as delta xe in the equation for inelastic drift, delta x. Therefore, the inelastic drift equals the occupancy factor, I, times the elastic drift, delta xe, divided by the deflection amplification factor, CD. The problem states the inelastic drift equals 6 inches. The occupancy importance factor, I, depends on the building use. Table 11.5-1 in ASCE 7 shows the occupancy importance factor depends on the occupancy category. Since the problem states the building is an office building, Table 1604.5 from IBC identifies office buildings as occupancy category type 2. Therefore, the occupancy importance factor equals 1.00. The deflection amplification factor, CD, is determined using Table 12.2-1 in ASCE 7. Since the seismic force resisting system of the building is a special moment resisting steel frame, CD equals 5.5. Plugging in the appropriate values into the equation below, the elastic drift equals 1.09 inches. Returning to our equation for the minimum height, h, we can substitute in the values for the elastic drift and the deflection amplification factor. The seismic base shear force, Vx, is the last unknown variable on the right-hand side of the equation. The seismic base shear force equals the seismic response coefficient, Cs, times the effective seismic weight, W. Assuming the load, P, is a permanent load, P equals the effective seismic weight, which equals 200 kips. And the problem statement provides the seismic response coefficient as 0.014. This makes the shear force equal to 2.8 kips. Plugging in all the appropriate variables into the right-hand side of the equation, The height calculates to 141.6 inches. Converting the height to feet by dividing by 12 inches per foot, the height equals 11.8 feet. As mentioned before, the stability coefficient is at most 0.10 for the p-delta effects to not be required to be considered for the seismic analysis. Smaller values of theta would result in increased heights. Therefore, the calculated value of h of 11.8 feet is indeed the minimum height of the structure for the p-delta effects to not be required to be considered. When reviewing the possible solutions, the answer is B.